Okay. So I'm very glad to introduce Hongjie Yu from IST Austria and announce his talk on number of cuspidal automorphic representations.
Thank you very much for the invitation. And the subject of the talk today is the number of cuspidal automorphic representations over a function field. So we start with field F, which is a global function field. And we, with A, the ring of adeles, and O, the ring of integral adeles. For a function field, there is no Archimedean places, so it's somehow easier than the number field, but we will see a different phenomenon than the number field. We suppose G is a split semi-simple group, or G is GLN. We could extend the work to split reductive group without difficulty. So this is only for simplicity. And T, we fix a split maximal torus. And we are interested in the cuspidal spectrum. So we're interested in the cuspidal spectrum, this one. We know it is a semi-simple representation of GA. And if we say a representation that shows up as a factor of this decomposition as a cuspidal representation. And one question is that given a representation rho, irreducible representation rho of GO, GO now is a maximal compact subgroup of G adele. We are interested in the question that how many pi contains rho. So we know that this number is finite, but when G equals GLN, we need to count up to an equivalent that pi is equivalent to pi up to a twist of the norm. And in the case of GLN, by multiplicity 1, we know that in this case, the cuspidal spectrum is multiplicity free. The interest of this question comes from several points. The first point is that there is a conjecture of Deligne on the counting problem of on the Galois side of this question that I will make more comments later. The second is that this question is related to the question of calculating the dimension of cusp forms. And the third thing is that when working with such questions, it helps us to understand Arthur's non-invariant trace formula. And for me, one surprising point is that the final result shows relation with Hitchin's moduli space, which is a key ingredient in the proof of Engel on fundamental lemma. So I will now make more precise comments on Deligne's conjecture. So Deligne's conjecture is mainly on the Galois side and for GLN. In this case, we choose a model, a curve for our function field. So we can choose this curve as good as possible. It can be smooth, it can be projective, and it can be geometrically connected. So it is just a model. And we choose a finite set of closed point A's, and we are interested in the problem of counting irreducible rank n analytic local systems over this open subset of the curve and with pre-described ramification in the point S. And so we're interested in the set En x minus s with pre-described ramification at each point. This is the set of irreducible rank n analytic local systems over x minus s. On this side, we have an action by pullback of Frobenius of the curve. So Frobenius act on it, and we are interested in the fixed point. We're interested in the number fixed by k iterated Frobenius action. This question, since local system is another terminology for Galois representation in some sense, and so using global Langlands correspondence established by Laurent-Laforgue, we can pass to automorphic side. And for the automorphic side, we are exactly interested in the question of the sum of cuspidal automorphic representation, which contains rho. So it means that rho isotypic part of pi is non-zero. For GLN, we have multiplicity 1, and we are interested in this number. And moreover, we are interested in this number for not only for A, but also for A base change to FQK. And when K is varying, it is expected that the number which is a series of number in K should be of the form as showed in this formula star. So that is to say that it should be a linear combination of Q Weiss numbers and with coefficients in integers. The Q Weiss numbers are they are just algebraic integers, so that with any embedding, the norm of this integer is something that is a Q's half integral power. And this M alpha is called the weight of the Q's base number. Typical example of such series of numbers satisfying this star is the number of FQK points of a variety defined over FQ. This is because the Weiss conjecture proved by Deligne and Grothendieck-Lefschetz fixed point formula. And for us, and for today's talk, we are interested in the case that Deligne described as easier to do. So it is with 10 regular ramifications, and the ramification forces any local system to be automatically irreducible. I will not focus on the Galois side, but I will explain what are these conditions on the automorphic side. So recall that we are interested in the sum of all cuspidal automorphic representations which contains a row. So where row is a representation, irreducible representation of GO. So which row we will use? It is report that O is the product of local integral rings, and so we can break row into a tensor product as local irreducible representations. For row V, we have a reduction map, and we can construct some irreducible representations on this finite group and then do inflation to GO. For this finite group, it is a finite group of Lie type. So we have the linguistic theory. Using the linguistic theory, we can fix for each V a pair, a maximal torus TV defined over kappa V, and a character theta V. Here, theta V is a character. I use a coefficient in C, but it's originally used coefficient in L-adic numbers. So we should fix isomorphism, and I will ignore this problem in the following talks. It's not important. And the other condition that we will impose on V is that we hope for any automorphic representation that contains row, it will be automatically cuspidal. And we will see that, in fact, most of such row constructed from the linguistic representation satisfy this condition. So we first see what row restricts pi in the Galois side. We know local Langlands correspondence for GON, and in fact, we have explicit local Langlands correspondence for essentially tame case due to Bushnell and Enyart. In this case, we suppose that the residue field of the local ring FV is, sorry. Yeah, so suppose that kappa V is a FQ prime, and let WV and IV be respectively the V group and the inertial subgroup. So for GON, we know that every maximal torus should be a product of restriction of the way, other way of GM. So the kappa V rational point of the torus TV should look like a product of finite extension of FQ prime of the residue field with the sum of the extension degree being n. And our row V is constructed from the linguistic representation of a character. So it is determined by the data TV and row V. The linguistic associate for any geometry conjugacy class of such pairs and conjugacy class in, now we are in GLN, so it is a conjugacy class in the dual of GLN, which is GLN itself. And suppose we are giving a irreducible representation pi of GLN FV, and we are, and suppose that sigma is the Langlands parameter that is associated to pi. So it is a representation of the Weare group times the SL2. Bushnell-Annihil's result is that if rho v is the linguistic type constructed from TV and theta v, then pi contains rho v if and only if it's a Langlands parameter sends a 10, if and only if its Langlands parameter is 10, and it sends a 10 generator to the conjugacy class that corresponds to the couple TV and theta v. So this explains why we use the linguistic representation and its relation with the Galois side. It is exactly the 10 regular case of the ramification of the Galois side. And another condition that I have supposed is so-called rho to be a cuspidal filter. So cuspidal filter is something that forces any automorphic representation which contains rho to be automatically cuspidal. In fact, most of such rho satisfy this condition. It's come from a simple observation. The first observation is that for a function field, fq, which is the constant field of the function field, is contained in any local ring. The second point is that given any Hacker character, we can factorize it as a product of local characters. And then, since it is a Hacker character, it is trivial on the field F, and F contains FQ. So in particular, it is trivial on FQ. But as we have a decomposition of chi into local components, so we know that the product of local components when restricting to FQ is trivial. So what we will apply this to irreducible representation is that if we have a irreducible representation of GFV, we can look at its central character. And we can do the same thing with factorizing of central characters. Then the central character, if pi contains rho v, its central character should be the restriction of theta v to the center. And I will make an example later. A corollary of a cuspidal filter is that for any rho, the rho isotypic part of the cuspidal spectrum equals exactly the rho isotypic part of L2 spectrum. So using rho, we can cut the discrete spectrum and the residue spectrum and the continuous spectrum. So here is an example that gives a cuspidal filter. So we consider GL2. And suppose kappa prime over kappa is a quadratic extension of finite fields. For GL2 over kappa, there are only two conjugacy classes of maximal tori over kappa. Only the first one is the split one, and the second one is the non-split one, because the Weare group now has only two elements. And so the first case is that if For example, for some point in S, here, I suppose that rho is a product, is a tensor product of V in S and rho V. So if for some point S in S, the torus is non-split, then by Deligne Lustig, we know that rho V is cuspidal. So for any irreducible representation of GFV, if it contains rho V, it implies that pi V is supercuspidal. While any automorphic representation that admits a supercuspidal local component is itself cuspidal. So in this case, every such rho gives a cuspidal filter. Another more interesting case is that each TV is split. In this case, the local component is no longer necessarily supercuspidal. And as shown by example, we suppose S consists of only a single point. And then TV is split, is isomorphic to GM square. Theta V then can be given by two characters, chi1 and chi2. In the linguistic theory, we have in the linguistic theory, we have some rho TV G theta V. If theta V is in general position, then this representation is irreducible. So in general position for this case says nothing else than chi1 does not equal to chi2. And in fact, for any such theta V, it is automatically a cuspidal filter. The reason is that if we have a non-cuspidal automorphic representation of GO2, then it must be a constituent of a parabolic induction of a Haeckel character. So if pi rho is not zero, then this lambda I should be unramified outside S, that means outside V. And the local component at V restricting to OV cross is nothing else than Xi, either Xi1 or Xi2. We can see this by looking at the supercuspidal support of this representation, because the supercuspidal support of pi must necessarily be given by lambda at this place. So, but we know that A cross embeds diagonally in A cross. It implies that the lambda 1, when restricting to FQ cross, equals to chi I. But either chi1 or chi2 are non-trivial, so this is impossible because, as we have said, lambda 1 is a Haeckel character. It is trivial on F cross, so it is trivial on FQ cross in particular. So this shows an example of a cuspidal filter, but it works in general. For any reductive group, we can see that most of the representation constructed from the linguistic representations are cuspidal filters. So to really calculate a number, to work with the number, we need to use Arthur's trace formula, more precisely the Arthur's non-invariant trace formula. For simplicity, we now consider G to be semi-simple, split as always. For any f which is compact support and smooth function, f acts by regular action on the L2 spectrum. And the spectral theory gives us a false equality that the trace of f on this L2 spectrum can be given by the integral of the kernel of this function. This is a false equality because both sides doesn't exist. The left-hand side is, the trace is usually not convergent and the integral does not convergent as well. So to have a true equality, Arthur truncates the kernel function so that the trace on the cuspidal part is unchanged. In this case, he defines, so he truncates the kernel function, this guy, I call it kfx, by something called, I call it kf smaller than 0. Its integral now has a sense. So I denote the integral by jf. Jf then on the spectral side is given by the trace of f on the cuspidal spectrum plus something. This something is minor, but it is a big problem when one really wants to apply trace formula to prove something. The good thing is that if rho is a cuspidal filter, when we want to calculate the number of cuspidal automorphic representations, this epsilon side can be ignored. So they are 0, in fact. So, but yes. So let rho be a absolutely regular representation, which means that for each rho v, it comes from a Linguistic representation. It's absolutely regular means that the pair TV theta v, it is in general position and it remains general position for any field extension. For any field extension, f q prime kappa v. I will explain why we need this condition later. Another condition is that if rho is a cuspidal filter, then we let E rho to be the trace function of rho. So by definition of the dual of rho, by definition, it is the trace of x inverse on rho when x lies in GO and to be 0 when x does not lie in GO. With this, the Arthur's non-invariant trace formula gives the number of cuspidal automorphic representation that we want to calculate. And why it gives the number comes from the absolutely regular part and the cuspidal filter part. With cuspidal filter part, we have no global problem. With absolutely regular part, we have no local problem. So I have explained the global problem lies in this tiny part. And so let's see what's the local problem and why we need rho to be absolutely regular. So the local aspect is that if the problem is that if we have a pi and we want to consider pi row, which is not 0 for such case, is equivalent that for every local component, pi v rho v is non-trivial. And it is then equivalent that the home set of rho v pi v is not 0. Well, with the trace function of rho v, we know that the trace of this function on pi v equals the dimension of the home set. So we really want this to be 1 to get the number. And this is explained by the, this phenomenon can be explained by the Hecke algebra of rho v. So let rho v, the Hecke algebra of rho v is defined as the anomorphism algebra of the compact induction of rho v to GV. We have a functor from the category of representation of GFV to this Hecke algebra modular. It sends pi v to the home set of rho v to pi v. And if pi v is irreducible, then it is sent to be a simple modular. The one theorem that I prove is that if TV theta v is absolutely regular, then theta v, so yeah, I repeat the definition. It means that theta v is in general position for any field extension. Then in this case, the Hecke algebra is commutative. Why we need Hecke algebra is commutative? Because if it is a commutative ring with finitely many generators, then its simple modulars are always dimensional 1. So with a corollary, we know that for any irreducible representation, GFV, the dimension of the home set from rho v to pi v is smaller than 1. So it is either dimension 0 or dimension 1. And this explains why the Arthur's non-invariant trace calculates the number we want to get. To announce the main result, we need to introduce some geometry object. And as well, it is also important to understand Arthur's non-invariant trace formula for over a function field. So now, as example, we still remains in the case that G is GON, F is a function field of a curve, and we need to fix a divisor on X. We introduced the algebraic stack MNE as the stack classifying a pair which consisting of E, which is a vector bundle of rank n and degree E, and theta is a bundle map from E to E twisted by the divisor. This is a huge algebraic stack because it is usually not of finite type. However, as it is used in the proof of fundamental lemma is the following Engel's observation that if we insert something special into the non-invariant trace formula for Lie algebra, then we get the FQ points of this algebraic stack. So the function that we are going to insert it into the formula is 1D. It is just the characteristic function of pi v minus nv. Here, PV is just a uniformizer of the local ring. With this special function, the FQ points of this stack. So first of all, what is FQ points of a stack? The difference between a stack and a variety is that a stack has not only points but also automorphisms for each point. So for a variety, the cardinality is just the sum that we taken over each point over 1. But for algebraic stack, its cardinality is not only taking into account of the points, but also its automorphism group. Okay. So with this definition of cardinality of a FQ point of a stack, we have a fake equality between the FQ points of the Hitchin's moduli stack and the integral of the Lie algebra analog of kernel function. As before, neither left-hand side nor right-hand side is finite. But Engel's observation is that we can restrict to elliptic part of both sides. On the left-hand side, we have Hitchin's fibration. So there is we can define an elliptic part, and which is of finite type now. On the right-hand side, the sum is over gamma in the Lie algebra GF. We can only consider the sum over gamma, which is elliptic F. Here, elliptic means maximal anisotropic. In this case, the sum is finite and the equality is a true equality. So as for its importance, we introduce this Lie algebra analog kernel function. It is just of the same form of the original one. Another observation found by Schrdingers, Lomont, and then Schrdingers is that Arthur's truncation has is very similar to the stability that one uses in geometry, because as I said, the left-hand side and the right-hand side of the Engel's observation do not exist. So for the geometric side, one defines a stability condition. It is on the other side, we have Arthur's truncation, and Schrdingers' observation for GLN is that these two coincide very well. So first of all, what is the semi-stability condition on the geometric side? Given a pair consisting of a vector bundle E and a theta of a bundle map from E to D twisted of E. It is semi-simple if we take any subpair f constitute f theta. So f is a subbundle of E, and theta is the restriction of theta on f. It is said to be semi-stable if, when taking the degree of f over the rank of f is smaller than the degree of the total bundle E to the rank of the total bundle E. So this defines the open substack of the huge stack MNE. And this open substack now, it is of finite type. Moreover, it admits a coarse moduli scheme. And this coarse moduli scheme is in fact a fine moduli scheme if the degree E is taken to be co-prime to the rank N. So fine moduli means that we have a coarse moduli and we have a universal family classifying things. So Schrdinger's observation is that taken the same test function as in the Engels observation, then with the Lie algebra analog of Arthur's truncation, we know that the cardinality of this smaller stack semi-stable part of Hitchin's moduli space equals the integral of this Lie algebra analog Arthur's non-invariant trace. So another very interesting theorem still due to Schrdingers is that for GLN, we can pass to Lie algebra. In this case, because for GLN, there is a problem of the center. For semi-simple group, the center is finite, but for GLN, the center is GM. So to have something reasonable, we need to restrict to a subset of GA. It is defined as the G in GLNA such that the degree of determinant of G equals E. With this, we can define we can restrict in the Arthur's truncated kernel to this smaller part for Lie algebra as well as for the group. And we have a coarse geometric expansion of GEF to following semi-simple conjugacy classes. For GLN, semi-simple conjugacy classes are parameterized by characteristic polynomials. So recall that KF X is GF F. When decomposing it, we just decomposing the sum following semi-simple conjugacy classes that gamma belongs to. Right. There is a tiny thing that we need to keep in mind is that usually over a positive characteristic, we don't have a Jordan decomposition. So it's not really a semi-simple conjugacy classes here. So except if we suppose the characteristic is large enough. Schrdingers vanishing theorem is that if we suppose, and which is crucial, that N and E is co-prime to each other, and we suppose that F has small support, it is supported in the maximal compact subset GO, then the the piece that which is not essentially unipotent is vanishes. So it means that essentially unipotent means that the semi-simple part of O is not in the center of G, ZG, FQ. And we also have a similar theorem for Lie algebra that we consider phi support in the all points of the Lie algebra of G. If for the Lie algebra analog GO, it also vanishes, its O is not essentially nilpotent. Here, nilpotent means that the semi-simple part is still in the center of the group. And one remark from the, which is almost trivial, but which is very useful, is that if we have phi to be the composition of F with the exponential map, then when restricting to unipotent, to nilpotent element, sorry, is nilpotent, then the nilpotent part equals the unipotent of the Lie algebra trace equals the unipotent part of the Arthur's non-invariant trace. And then using Schrodinger's vanishing theorem, one can relate the whole trace of the group with its Lie algebra. So I can announce the result now. The result is that for GLN, if S is the set of ramification, for simplicity, I suppose S consists of FQ points. So in other words, I suppose the residue field of the point in S are FQ. So they are, yeah. And let Kx be any canonical divisor. The special divisor D we're going to use is Kx plus the sum over points in S. We have a residue morphism from from the semi-stable Hitchin's moduli space to the product of the space of characteristic polynomials. And so this is the right-hand side is the fiber of the global characteristic polynomials. I only consider it's the coefficients, those coefficients lie in FQ. I will not make more comments on this residue morphism, but with this morphism, we have the following theorem. Suppose that rho is of Deligne Lustig type as we constructed before, and is absolutely cuspidal filter. It means that for it not only a cuspidal filter, but also cuspidal filter under finite field extensions of FQ. So if the character theta v, when restricting to the center of G, is trivial, then there is no pi contains rho. And otherwise, we can take degree E coprime to N. We have the number up to equivalence of cuspidal automorphic representations for GLN equals the fiber of the residue map in O up to a Q's power. Here, O is any point in the space of characteristic polynomials if the torus is isomorphic to FQ_N1 times FQ_Nk, then we need to take characteristic polynomial to be F1t, Fkt, such that the degree of Fit are Ni, and they are 2 by 2 distinct. In particular, the right-hand side of the equality is of the form that Deligne expects. So in this case, it proves Deligne's conjecture. But yeah, I only mention one key point in the proof. As we have seen that many results are due to Schrdingers. The key point is that, so first of all, we have Arthur's non-invariant trace. When we use the test function to be the trace function of rho, then, and rho is a cuspidal filter, absolutely regular. For GLN, absolutely regular equals regular. So in this case, the non-invariant trace already gives the number of cuspidal automorphic representations. And in this case, and we also have seen the result of Schrdingers that the cardinality of the Hitchin's moduli space is related to the trace formula over Lie algebra. And his vanishing theorem allows us to reduce the unipotent part for the group case and the nilpotent part for the Lie algebra case. Hence, we can relate two versions of a trace formula by any exponential map. However, both result requires special test function. So we need to compare them by changing test function. So why can we change test function? We use Kashtan's Springer hypothesis. So Kashtan proves that any finite finite reductive group, if we consider the linguistic induction of a trivial character, so we get Green's function. When we restricting Green's function to unipotent elements, and we know that it is the Fourier transform of it is a Fourier transform of the characteristic function of a regular conjugacy class. And this regular conjugacy class is anything that lies in the Lie algebra of the torus TV. And this is the key point that we can use to transfer to change test functions by using a Poisson summation formula. So some corollaries of the main result is that the numbers that of cuspidal automorphic representations depends only in the torus TV, so in the conjugacy class of torus TV, but not in theta v, as long as theta v is in general position. The second, that with Engel's result, I prove that the fiber of the residue map in O is always geometrically irreducible when O is regular. And moreover, we have another result which is more of analytic nature, because for a variety of which is irreducible, we know that its number of points is of this form, Q dimension V plus something. And so as we know the dimension of the Hitchin's moduli space, so we have an estimate for the number of cuspidal automorphic representations when Q tends to infinity. So all of these stories are about GLN, and it depends crucially on Schrdingers' vanishing theorem that if we take E to be co-prime to N, then we can pass to unipotent and nilpotent part. However, for general reductive group split, we don't have such a possibility to fix a degree of the point. So how to deal with a split reductive group? The goal is to generalize the previous result to split reductive groups. The difficulty, as I've said, is that we don't have Schrdingers' vanishing theorem. And the idea that I use comes from geometry. In geometry, when study the geometry of the moduli space of vector bundles and Hitchin's moduli space, one usually adds parabolic structures at some points and then define semi-stability with an extra parameter related to the extra parabolic structure that we have added. So I adopt this strategy to trace formula with an extra parameter C. I introduced two distributions, JC and JLC. With this variant, it works similar as the GLN case when we restrict to degree E co-prime to N. So for simplicity, suppose G is split semi-simple. And first thing is that, as in Arthur's trace formula, JC does not truncate the trace on the cuspidal spectrum. The second thing is that we still have a coarse geometric expansion. So here, following semi-simple conjugacy classes in GF, although we don't have Jordan decomposition, we can put those elements which doesn't admit a Jordan decomposition into one single classes. And we show that we still have a well-defined coarse geometric expansion. So I have a similar vanishing theorem as Schrdingers ones. So fix a point infinity and let C in general position in some sense that is not orthogonal to the roots, to any roots. So if the support is very small, so that it is contained in outside infinity, it's contained in GO. In infinity, it is contained in the Iwahori subgroup. So here is Iwahori subgroup. Then I show that the contribution for almost every semi-simple conjugacy class are 0, except if the conjugacy class can be represented by an elliptic element lying in the split torus. So in this case, I show that moreover, I can relate the contribution of this A related to this conjugacy class of A's to the contribution of conjugacy class of 1, but for a different group, for GS0. So we can make decent rank of the group. And if one interesting remark is that if Q minus 1 is divisible enough, for example, if 360 divides Q minus 1, then any geometric elliptic elements in which lies in the TFQ bar are in fact contained in TFQ. So it is something irrelevant to the field extension. For Lie algebra, I show something similar that we also has a coarse geometric expansion, and if the support of the function is small, then because a difference from a Lie algebra and a group is that in a split torus, there is no elliptic element because the centralizer of any semi-simple element in the split torus is a Levy subgroup. So in this case, there is no elliptic element, and we are reduced to nilpotent contribution. And I show that it has closed relation with geometry. That in geometry we have, as I've said, we have a parabolic Hitchin's moduli space that for each point x, one adds a parabolic structure and a stability parameter and defines a semi-stable part for this parabolic version of Hitchin's moduli space. So with a special test function that is defined as the characteristic function for x outside S, it is GO up to a twist, and for V in S, it is the characteristic function of the Iwahori algebra. Then with this test function, the trace I defined gives the FQ point of the parabolic version of Hitchin's moduli space. And we also have a trace formula for Lie algebra. So I use a parenthesis because it is neither side gives a trace of anything. It is just that the distribution F, the distribution for Lie algebra equals on F equals is the distribution on the Fourier transform of F up to a constant depending on the Hacker algebra. Depending on the Haar measure. So the semi-simple case of my theorem is that suppose that P is very good, defined by Schrdingers and Sternberg. So usually it means P larger than 5 is okay. And Q minus 1 is very divisible. So to have the method work, I mean, to have something that calculates the number of cuspidal automorphic representations, I need the torus T infinity split at least for 1 point. And so, but for simplicity of this talk, I suppose that every TV which defines the linguistic representation is split. So it means that the rho V we are considering are principal series. And let rho still be a cuspidal filter. So I define something called elliptic split co-endoscopic group. I call it co-endoscopic because it is endoscopic group of the dual of G. And then for each such group, there exists an integer so that the number we're looking for can be written as a linear combination of the number of parabolic Hitchin's moduli space up to a q's power. But there is a subvariety inside this parabolic Hitchin's moduli space, which gives this number up to q's power. So q's power is not important. And but to have more information on the coefficient NH, the first thing we know that is the sum of NH is bounded. The second thing is that because motivated by Deligne's conjecture, we are interested in the behavior of this number when Q extends to FQ extends to FQK. So if theta V is algebraic, I prove that NH are unchanged. And as in the GLN case, the number of cuspidal automorphic representation in this case has a asymptotic formula given by a q's power and multiplied by the center of G and the fundamental group of G, algebraic fundamental group. The other point is that the H showed up in these formula, which are called elliptic split co-endoscopic groups. They can be described in terms of purely in terms of root system of G. In particular, there are only finitely many of them. And that's all for my talk. Thank you for your attention.
Thank you very much. Questions, please.
So can you just recall these constants that you had in front? I mean, where do they come from? This NA?
Which one?
On the right-hand side, the NA.
The formula, yes.
Yeah. The NH, the integer.
Yes, the integer, yeah.
Where do they come from? What's the nature?
They are, yeah, when defining the linguistic representations, I use theta V, and the NH is a sum of theta V at some point. Yeah. So the sum over some special elements. So lies in S, but not all of them. Only a small part of TFQ. So.
But ultimately, they only depend on H. Is that so?
No, it depends on H and it depends on theta V. So, yeah. But it does not depend on theta V totally. It only depends on its position in some sense. So we have we can look at the Weare chamber of with which theta v lies in. It depends only on that.
Okay, another question. Maybe I asked you before, but I forgot. So, is there any hope to go beyond the depth zero? I mean,
yes. Yes. There is no. I think there are some possibilities but we need to use type theory, and so for rho v, sometimes we can replace it by other representations of positive depths, but to construct such rho v, we need to use type theory, and there when using Joe Yu's type theory, I think there is a possibility to pass to Lie algebra, and we can have similar results. The right-hand side will be replaced by the Hitchin's moduli space with which does not have simple poles but have multiple poles. Yeah, this is totally possible, and I'm working on it for the moment.
Okay, very nice.
Any further questions? Okay, let us thank the speaker again. So in next time we don't have a talk. We have kind of semester break here, but so we will resume in March. Hopefully on March 2, I will send an announcement.